Okay, so it's a pleasure to see all of you guys. I'm Justin. I'm your third instructor for 6006. This is my first time with this course, although of course this is material that we all know and love in computer science department. I'll admit I find the prospect of teaching sorting to 400 people all at once kind of low-key terrifying, but we're going to give it a shot, and hopefully that'll subside as the lecture goes on today, all right? So we're going to pick up where we left off in our last lecture and continue on with the similar theme that we're going to see throughout our algorithms class here in 6006. I think Jason and colleagues have done a really great job of kind of organizing this class around some interesting themes. So I thought I'd start with just a tiny bit of review of some key vocabulary words. Incidentally, typically I teach the intro graphics class, a geometry course, and last year I got feedback that said I have serial killer handwriting. I'm not 100% sure what that means, but we're going to use the slides a tiny bit more than normal just to make sure you guys can read. And when I'm writing on the board at any point, if you can't tell what I wrote, it's definitely me and not you, so just let me know. But in any event, in 6006, all the way back in our lecture one, I know that was a long time ago, we introduced two big keywords that are closely related but not precisely the same. Hopefully I've gotten this right. But roughly, there's a theme here, which is that there's an object called an interface, right, which is just sort of like a program specification, right? It's just telling us that there's a collection of operations that we want to implement. So for example, a set, as we're going to see today, is like a big pile of things. And behind the scenes, how I choose to implement it can affect the runtime and sort of how efficient my set is, but the actual way that I interact with it is the same, whether I use an unsorted array, a sorted array, or what have you. On the other hand, what happens behind the scenes is something called a data structure, which is a way to actually, in some sense, implement an interface, right? So this is an object that on my computer is actually storing the information and implementing the set of operations that I've laid out in my interface, right? And so this sort of distinction, I think, is sort of a critical theme in this course because, for instance, in the first couple weeks, we're going to talk about many different ways to implement a set. And we're going to see that there's a bunch of trade-offs, right? Some of them are really fast for certain operations and slow for others. And so essentially, we have two different decisions to make when we choose an algorithm. One is making sure that the interface is correct for the problem that we're concerned with. And the other is choosing an appropriate data structure whose efficiency and memory usage and so on kind of aligns with the priorities that we have for the application we have in mind. So hopefully this kind of high-level theme makes sense, and really kind of spiritually, I think, that's sort of the main message to get out of this course in the first couple of weeks, even though all these O's and thetas and so on are kind of easy to lose the forest through the trees. In any event, today in our lecture, we're concerned with one particular interface, which is called a set. Set is exactly what it sounds like. It's a big pile of things. And so a set interface is sort of like an object that just you can keep adding things to it and then querying inside of my set, is this object here? Can I find it? And then maybe I associate with my objects in my set different information. So for example, maybe I have a set which represents all the students in our classroom today. Yeah, and all of you guys are associated with your student ID, which I believe at MIT is a number, yeah, which has a less than sign, which is convenient, so we can sort all of you guys. And that might be the key that's associated to every object in the room. And so when I'm searching for students, maybe I enter in the student number, and then I want to ask my set, does this number exist in the set of students that are in 6006? Right? And if it does, then I can pull that student back, and then associated with that object is a bunch of other information that I'm not using to search. So for instance, your name, your I don't know, your social security number, credit card number, all the stuff that I need to have a more interesting profession. So in any event, let's kind of fill in the details of our set interface a little bit more. So our set is a container, right? It contains all of the students in this classroom, in some virtual sense at least. And so to build up our set, of course, we need an operation that takes some iterable object A and builds a set out of it, right? So in other words, I have all of the students in this classroom represented maybe in some other fashion, and I have to insert them all into my set. I can also ask my set for how much stuff is in it. Personally, I would call that size, but length is cool too. And then, of course, there are a lot of different ways that we can interact with our set. Right? So for instance, we could say, is this student taking 6006? So in set language, one way to understand that is to say that the key right? Each person in this classroom is associated with a key. Does that key k exist in my set? In which case, I'll call this find function, which will give me back the item with key k, or maybe like null or something if it doesn't exist. Maybe I can delete an object from my set or insert it. Notice that these are dynamic operations, meaning that they actually edit what's inside of my set. And then finally, there are all kinds of different sort of operations that I might want to do to interact with my set beyond is this thing inside of it, right? So for instance, maybe, okay, so for the student ID example, probably finding like the minimum ID number in a class isn't a terribly exciting exercise, but maybe I'm trying to find the student who's been at MIT the longest, and so that would be a kind of reasonable heuristic. Actually, I have no idea whether MIT student IDs are assigned linearly or not, but in any event, I could find the smallest key, the largest key, and so on in my set. And these are all kind of reasonable operations to query where my object is just a thing that stores a lot of different entities inside of it. Now, is this description here, notice that I've labeled this as the set interface. This is not a set data structure. Right? And the way to remember that is that I haven't told you how I've actually implemented this, right? I haven't told you that, I'm going to, behind the scenes, have an array of information and look inside of it, and that's how I'm going to implement, find min or find max with a for loop or whatever. All I'm telling you is that a set is a thing that implements these operations, and behind the scenes, my computer does what it does. That might sound abstract, but it's more or less what you guys do when you write code in Python, right? You have, I think in Python, what we're calling a set is maybe a dictionary. I'm a MATLAB coder. I'm sorry. I'm a numerical analysis kind of guy. But essentially, one of the beautiful things about coding in these high-level programming languages is that they take care of these ugly details, and what you're left with is just the kind of high-level interfacing with this object that you need at the end of the day. So of course, in today's lecture, now that we've set out our goal, right, which is to fill in, like if I wanted to write code for a set, how could I do it? Now, of course, our goal is to give different data structures that implement these and then understand them in terms of their efficiency, data storage, correctness, all that good stuff. So before we get into all these ugly details, let me pause for a second. Are there any questions about this basic interface? Y'all should feel free to stop me anytime because this is going to be hella boring if you're not getting the first slide or two. Yes?
Can you explain how insert works as in, like they're replacing with the as in, like, you're adding this element X to the set, but what is its state?
That's a fabulous question. So the question was, what exactly is this insert operation doing? Yeah, so I think working in the analogy of the students in this classroom is kind of a reasonable one. So I'm going to build up an object, which is a student. Right? So in this lecture notes, I think we've been consistent. I caught one or two typos. We're going to think of X as the object that contains all of the information. And then associated with that is one piece, which is called the key. That's where we're going to use the letter K. Right? And that's like your student ID. That's the thing I'm going to use to search. Right? So what the insert operation does is it takes this whole student object X, which includes your ID, your name, your phone number, all that good stuff, and it inserts it into the set with the understanding that when I search my set, I'm going to be searching by key. Right? So when I want to find a student, I have to put in my ID number. Does that make sense? Cool. Any other questions? That's great. Fabulous. Okay, so now let's talk about how to actually implement this thing. And thankfully, we're already equipped with at least a very simple way that we can implement a set based on what you've already seen in your previous programming classes or even in just in the last two lectures, which is one way to understand a set, or to implement it rather, would be to just store a giant array of objects that are in my set. I suppose continuing with the sort of theme of the last two lectures, this is not a space in memory, but rather a metaphorical array, in a theoretical sense. But it doesn't really matter. And so one way to store my set would be to just store a bunch of X's in no particular order. Does that make sense? So I have a big piece of memory. Every piece of memory is associated with a different object in my set. Obviously, this is quite easy to build, right? I just make a big array and dump everything in there. And the question is this particularly efficient or useful way to implement a set? Right, so for instance, let's say that I have, I have a set of all the students in this classroom. There's like some ridiculous number of you guys, so actually, asymptotic efficiency maybe actually matters a little bit. And I want to query, does this student exist in my class? Is Eric Domain taking 6006? The answer is no, I think. Teaching, taking, I don't know. But in any event, how do I implement it if my set is unordered? We'll think about it for a second. Yeah?
Sort the set into some sort of order, and then afterwards we can query the set as order.
It's actually an interesting suggestion, which is going to anticipate what's happening later in this lecture, which was to sort the set and then binary search, right? But let's say that actually I only have to do this once. For some reason, I build up a whole set of the people in this classroom, and I just want to know, is Eric Domain in this class, right? So then that algorithm would take n log n time, right? Because I've got to sort everybody. And then I have to do binary search, which is maybe log n time. But I claim that if the only thing I care about is building up my entire set and searching it once, there's actually a faster algorithm. This is going to be needlessly confusing because we're going to see that this is really not the right way to implement it in about 38 seconds. Yes? Yeah, just iterate from beginning to this array and say, is this guy Eric? No. Is this guy Eric? No. Is this guy Eric? Yes, and then return him, right? So in the worst case, how long will that algorithm take? Well, in the worst case, I have really bad luck, and your instructor is all the way at the end of the list, right? So in this case, what is that going to mean? That means that I have to walk along the entire array before I find him, so that algorithm takes order n time. And so your colleague's intuition that somehow this is quite inefficient is absolutely correct, right? If I know that I'm going to have to search my array many, many times for different people, then probably it makes sense to do a little bit of work ahead of time, like sorting the list, and then my query is much more efficient. But this is all just to say that an unordered array is a perfectly reasonable way to implement the set interface, and then searching that array will take linear time every single time I search. Yeah? And of course, if you go down your list of all of the different operations you might want to do on a set, you'll see that they all take linear time. So for instance, how do I build my set? Well, I have to reserve n slots in memory, right? And at least according to our kind of model of computation in this class, that takes order n time, right? Then I've got to copy everything into the set. Similarly, if I want to insert or delete, what do I have to do? Well, I have to reserve memory and stick something inside of there in the worst case. We saw this amortized argument before, if your set is allowed to kind of grow dynamically. And finally, if I wanted to find the minimum student ID in my classroom, sort of the only algorithm I can have if my list of students isn't sorted is to what? Just iterate over every single student in the class, and if the guy that I'm looking at has a smaller ID than the one that I found, replace it. Does that make sense to everybody? So basically, everything you can do in a set, you can implement, and I think all of you guys are more than qualified to implement as an unordered array. It's just going to be slow. Yes? Yeah, that's right. So I don't know in this class, if you're, I guess the set interface, the way that we've described it here is dynamic. We can just keep adding stuff to it. In that case, remember this amortized argument from Eric's lecture says that on average, that will take order n time. What was that? Oh, that's true. That's an even better, sorry. Even if it weren't dynamic. If I wanted to replace an existing key, like for some reason 2 students have the same ID. This is a terrible analogy, I'm sorry. But in any event, if I wanted to replace an object with a new one, well, what do I have to do? I'd have to search for that object first and then replace it. And that search is going to take order n time from our argument before. Thank you. OK, so right. In some sense, we're done, right? We've now implemented the set interface. Life is good. And of course, this is the difference between existence and actually caring about the details inside of this thing, right? We've shown that one can implement a set, but it's not a terribly efficient way to do it by just storing a big, hot mess, disorganized list of numbers without any order. Yeah? So instead of that, conveniently, our colleague in the front row here has already suggested a different data structure, which is to store our set not as just a disorganized array in any arbitrary order, but rather to keep the items in our set organized by key. Right? So in other words, if I have this array of all of the students in our classroom, and the very first element in my array is going to be the student with the smallest ID number. The second is the second smallest ID number, all the way to the end of the array, which is the student with the biggest ID number. Now, does that mean I want to do arithmetic on student ID numbers? Absolutely not. But it's just a way to sort of impose order on that list so that I can search it very quickly later. Okay, so if I want to fill in the set interface, and I have somehow a sorted array of students, right? So again, they're organized by student ID number, then my runtime starts to get a little more interesting. Yeah, so now insertion, deletion still take the same amount of time. But let's say that I want to find the student with the minimum ID number, right? This find min function. Well, how could I do it in a sorted array? Keyword is sorted here. Where's the min element of an array? Yes? Yeah, in fact, I can give a moderately faster algorithm, which is just look at the first one, right? If I want the minimum element of an array, and the array is in sorted order, I know that's the first thing, right? So that's order one time to answer that kind of a question. And similarly, if I want the thing with the biggest ID number, I look all the way at the end. Now, in 600, this MIT student class numbers are super confusing to me. In 6001, 6042, you guys already, I think, learned about binary search and even may have implemented it. So what do we know? If my array is sorted, how long does it take for me to search for any given element? Yes? Log n time. That's absolutely right? Because I can cut my array in half. You know, if my key is bigger or smaller, then I look on the left or the right. And so this is a much more efficient means of searching a set. Yeah? So in particular, you know, 6006 this year has 400 students. Maybe next year it has 4,000. You know, eventually it's going to have like billions, right? Then what's going to happen? Well, if I use my unordered array, you know, and I have 1 billion students in this class, it's going to happen. Well, then it's going to take me roughly 1 billion computations to find any one student in this course, whereas log of 1 billion is a heck of a lot faster, right? On the other hand, I've kind of swept a detail under the rug here, which is how do I actually get a sorted array to begin with? And what we're going to see in today's lecture is that that takes more time than building it if I just have a disorganized list, right? Building a disorganized list is an easy thing to do. You probably all do it at home when you're cleaning house, yeah? But actually sorting a list of numbers requires a little bit more work. And so this is a great example where there's at least a tiny amount of trade-off, right? Where now building my sorted array to represent my set is going to take a little more computation. We're going to see it's n log n time. But then once I've done that, sort of at step 0, now a lot of these other operations that I typically care about in a set, like searching it for a given key, are going to go a lot faster using, you know, binary search. Okay, so this is our basic sort of motivator here. And so now we've seen the set interface in 2 potential data structures. And our goal for the day is going to be to kind of fill in the details of that second one. And since you all have already seen binary search, you've probably also already seen sorting. But in any event, today we're going to focus mostly on the sort of lower left square here, right? On just how can I take a disorganized list of objects and put it into sorted order so that I can search for it later. Right? So in other words, our big problem for lecture today is this second thing here, right? Just sorting. Incidentally, in the next couple lectures, we're going to see other data sets, or data structures rather. Sorry, data structs. I used to teach machine learning class, and we'll see that they have different sort of efficiency operations that we can fill in this table. So we're not done yet, but this is one step forward. Okay. So hopefully I have sort of ad nauseum justified why one might want to sort things. And indeed, there are a couple of vocabulary words that are worth noting. So remember that your sorting algorithm is pretty straightforward in terms of how you specify it, right? So in sorting, your input is an array of n numbers. I suppose actually really we should think of them like keys. It's not going to matter a whole lot. Right? And our output, I'm always very concerned that if I write on the board on the back, I have to cover it up. It's going to be out. It's going to be a sorted array, right? And we'll call this guy B, and we'll call this one A. This classroom is not optimized for short people. Okay, so there's a lot of variations on the basic sort of sorting problem and the different algorithms that are out there. 2 vocabulary words I'm going to highlight really quick. One is if your sort is destructive, what that means is that rather than like reserving some new memory for my sorted array B and then putting a sorted version of A into B, a destructive algorithm is one that just overwrites A with a sorted version of A. Right? So a lot of like, certainly the C++ interface does this. I assume the Python one does too. I always forget this detail. In addition to destructive sorts, some sorts are in place, meaning that not only are they destructive, but they also don't use extra memory in the process of sorting. Right? Like you could imagine a sorting algorithm that like has to reserve a bunch of like scratch space to do its work and then put it back into A. Right? Like, for instance, the world's dumbest destructive sort might be to call your non-destructive sort and then copy it back into A. Right? But that would require order n space to do. So if my algorithm additionally has the property that it doesn't reserve any extra space, at least up to a constant, then we call that in place. Okay, so those are our basic vocabulary words, and there are ways to kind of understand the differences between different sorting algorithms. Yes? Why do they end up using extra O1 space? Oh yeah, sure. Like any time I just make a temporary variable like a loop counter, that's going to count toward that order 1. But the important thing is that the number of variables I need doesn't scale in the length of the list. Yep. Okay, so I present to you the beginning and end of our sorting lecture, which is the world's simplest sorting algorithm. I call it permutation sort. I think it's very easy to prove correctness for this particular technique. So in permutation sort, what can I do? Well, I know that if I have an input that's a list of numbers, there exists a permutation of that list of numbers that is sorted. Kind of by definition, right? Because a sort is a permutation of your original list. So what's a very simple sorting algorithm? Well, list every possible permutation, and then just double check which one's in the right order. Yeah? So there's sort of two key pieces to this particular technique if we want to analyze it. I don't see a reason to belabor it too much. But there's sort of one is that we have to enumerate the permutations. Now, if I have a list of n numbers, how many different permutations of n numbers are there? Yes? N factorial, right? So just by virtue of calling this permutations function, I know that I incur at least n factorial time. It might be worse, right? It might be that like actually listing permutations takes a lot of time for some reason. Like every permutation itself takes order n time. But at the very least, you know, each one of these things looks like n factorial. I warned you, my handwriting is terrible. Right, so that's what this omega thing is doing, if I recall properly. And then secondarily, well, we've got to check if that particular permutation is sorted. How are we going to do that? Well, there's a very easy way to check if a list is sorted, right? I'm going to do maybe for I equals 1 to n minus 1. Notice not a Python coder. It's going to look a little different, right? Then check, you know, is b I less than or equal to b I plus 1, right? And so if this relationship is true for every single I, that was supposed to be a question mark, right? This was less than or equal to with a question mark over it. It was my special notation, right? So if I get all the way to the end of this for loop and this is true everywhere, then my list is sorted and life is good, right? So how long does this algorithm take? Well, it's kind of staring you right in the face, right? Because you have an algorithm which is looping from 1 to n minus 1. So this step incurs order n time, gets theta of n time, because we've got to go all the way to the end of the list. So when I put these things together, permutation sort, well, remember that this check if sorted happens for every single permutation. So at the end of the day, our algorithm takes at least n factorial times n time. It's a great example of something that's even worse than n factorial, which somehow in my head is like the worst possible algorithm. Yeah? So do you think that Python implements permutation sort? I certainly hope not. Yes? Right, so the question was, why is it omega and not big O? Which is a fabulous question in this course. So here's the basic issue. I haven't given you an algorithm for how to compute the set of permutations for a list of numbers. I just kind of call some magic function that I made up. But I know that that algorithm takes at least n factorial time in some sense, or if nothing else, the list of permutations is n factorial big, because that's all the stuff I have to compute. So I haven't told you how to solve this problem, but I'm convinced that it's at least this amount of time. So remember that omega means lower bound, right? So when I put it all together, in some sense, okay, this isn't satisfying in the sense that I didn't give you precisely the runtime of this algorithm, but hopefully I've convinced you that it's super useless. Yeah. Okay, any other questions about that? But great, so if we go back to our table for the set interface, well, in some sense, if we implemented it using this goofy algorithm, then the lower left entry in our table would be n factorial times n, which wouldn't be so hot. But notice that actually all the rest of our operations are now quite efficient, right? I can use binary search. I just obtained the algorithm that I obtained the sorted array in kind of a funny fashion. Okay, so let's fill in some more interesting algorithms. As usual, I'm talking too much, and I'm nervous about the time, but we can skip one of them if we need to. Okay, so how many of us have seen selection sort before? I see your hand, but we're going to defer for a little bit. I'm sorry? That's fabulous. Why don't we defer to the end of lecture, and we'll do it then. Okay, so the first algorithm that we'll talk about for sorting, which is somewhat sensible, is something called selection sort. Selection sort is exactly what it sounds like. So let's say that we have a list of, oops, my laptop and the screen are not agreeing. Okay, let's say I have a list of numbers 82493. This is a message that Jason, I think, is sending me in the course notes, but I haven't figured it out. But in any event, and I want to sort this list of numbers. Here's a simple algorithm for how to do it, which is I can find the biggest number in this whole list and stick it at the end. Yeah? So in this case, what's the biggest number in this list, everybody? 9. Good. See, this is why you go to MIT. Okay, so I'm going to take that 9, I'll find it, and then swap it out with the 3, which is at the end. And now what's my sort of inductive hypothesis? Well, in some sense, is that everything to the right of this little red line that I've drawn here is in sorted order. In this case, because there's only one thing. Yeah? So now what am I going to do? I'm going to look to the left of the red line, find the next biggest thing. What's that? Oh, come on. There we go. Yeah, wake up. Okay, so right, so the next biggest one is the 8, so we're going to swap it with the 3, put it at the end, and so on. I think you guys could all finish this off. I suppose there should be one last line here where everything is green and we're happy, but in some sense, we're pretty sure that an array of one item is in sorted order. And so essentially, from a high level, what did selection sort do? Well, it just kept choosing the element, which was the biggest, and swapping it into the back, and then iterating. Now, in 6006, we're going to write selection sort in a way that you might not be familiar with. In some sense, this is not so hard to implement with 2 for loops. I think you guys could all do this at home. In fact, you may have already. But in this class, because we're concerned with proving correctness, proving efficiency, all that good stuff, we're going to write it in kind of a funny way, which is recursive. Now, I can't emphasize strongly enough how little you guys should implement this at home. This is mostly a theoretical version of selection sort, rather than one that you would actually want to write in code, because there's obviously a much better way to do it, and you'll see that in your recitation this week, I believe. But in terms of analysis, there's a nice, easy way to write it down. So we're going to sort of take the selection sort algorithm, and we're going to divide it into 2 kind of chunks, right? One of them is find me the biggest thing in the first k elements of my array. I shouldn't use k, because that means key. The first I elements of my array. And the next one is to swap it into place and then sort everything to the left, right? That's sort of the 2 pieces here. So let's write that down. Right. So what did I do? Well, in some sense, in step 1 here, I found the biggest with index less than or equal to I, right? So I started at the end of the list and then kind of moved backward, right? And then step 2 was to swap that into place. Notice when I say swap, so for instance, when I put the 8 there, well, I had to do something with that 3, so I just put it where the 8 used to be. And then finally, well, am I done? No, I just put the biggest thing at the end of my array. So now I have to sort from index 1 to I minus 1, right? Because now I know that the last guy is in sorted order. I see. I'll return to you in just a second. So yes. You can't read the handwriting. This is index less than or equal to I. Great question. I warned you, it's going to be a problem. Okay. So let's do step 1 first. So I'm going to put code on the board, and then we're going to fill in the details. Eric is posting on Facebook. I'm going to turn that feature off on my watch later. Okay, so right, let's implement this helper function here. This is something we're going to call prefix max, and this is going to find me the biggest element of an array between index 0 and index I, inclusive, I believe. Yeah. Well, here's an interesting observation, really a deep one, which is that the biggest element from 0 to I, that's an I, sorry, there's sort of 2 cases, right? Either it's at index I, meaning like I have the first 10 elements of my array. Either it is element number 10, or what's the other case? It ain't. Yeah? In other words, it has index less than I. This is kind of a tautology, right? Like either the biggest thing is at this index or it's not, in which case it has to be to the left. Does that make sense? So this gives us a really simple algorithm for finding the biggest element in the array between index 0 and index I, which is what I've shown you on the screen here. I'd write it on the board, but I am a slow writer and already low on time. And so essentially, what did I implement? Well, I found the biggest element between index 0 and index I minus 1. Right? So if I have, let's say that I have an array, I forget the sequence of numbers, like 8, 3, 5, 7, 9. That'll do it. Yeah? And so like I give a pointer here, which is I. Right? Then the very first thing that I do is I compute the biggest number all the way to the left of this stuff. In this case, that is 8. There we go. Now, I look at the very last element of my array, which is 9. You're killing me today, guys. Okay? And then what do I return? Well, I want the biggest one between 0 and index I. So in this case, I return the 9. Does that make sense? So, you know, there's this, I know Jerry Kane at Stanford likes to talk about the, what is it, the recursive leap of faith that happens. Another term for this is induction, right? So if we want to prove that our algorithm works, well, what do we have to do? We have to show that when I call this function, it gives me the max of my array between index 0 and index I for all I. Right? So let's maybe do this inductive proof a little bit carefully, and then the rest will be sloppy about it. Right? So the base case is I equals 0. Right? Well, in this case, there's only one element in my array, so it's pretty clear that it's the max. Right? Okay. And now we have to do our inductive step. Right? Which means that if I call prefix max with I minus 1, I really do get the max of my array between 0 and index I minus 1. And then really, I can just look at my proof, my very deep statement, which is that either my object is at the end of the array or it's not. And this is precisely what we need to justify the inductive step. Right? Essentially, there are 2 cases. Either the biggest element in my array is the last one, or it's not. We already, by our inductive hypothesis, have argued that our code can find the biggest element between index 0 and index I minus 1. So as long as we take the max of that and the very last guy, we're in good shape. Okay, so this is our sort of very informal proof of correctness. Okay, so now we have to justify runtime for this algorithm. And that's like actually not 100% obvious from the way I've written it here. Right? There's no for loop. But what do I do? Well, in some sense, if my runtime is a function s, well, for one thing, if my array has one element in it, well, my runtime, it might be 7, it might be 23, but at the end of the day, it only does one thing. It just returns I, right? So in other words, it's theta of 1. This isn't terribly insightful, but what else do we know? Well, when I call my function, I call it recursively on one smaller index, and then I do a constant amount of work. So I know that S of n is equal to S of n minus 1 plus theta of 1, right? I do a little bit of extra computation on top of that. Anybody guess what this total runtime is going to be? Yes? Yeah, order n, right? And so let's say that we hypothesize that this takes n time. You kind of see that, right? Because like at step n, we call n minus 1, we call n minus 2, and so on, all the way down to 1, right? If we want to prove this, one of the ways that we, I think in theory you guys have learned in the past and you're going to cover in recitation, is a technique called substitution. What we do is we're going to look at this relationship and we're going to hypothesize that we think S of n maybe looks something like Cn for some constant c that doesn't depend on n. Then all we have to do is double check that that relationship is consistent with our inductive hypothesis, or rather just this recursive function. And if it is, then we're in good shape. Yeah, so in this case, well, what do I know? I've guessed that S of n is theta of n. So, in particular, if I plug into this recursive relationship here, on the left-hand side, I'm going to get Cn. On the right-hand side, I'm going to get Cn minus 1 plus theta of 1. And we just have to make sure that this is like an OK equal sign. So what can I do? I can subtract Cn from both sides. Maybe put that 1 on the other side here. I'm going to get that C equals big O of 1. C is, of course, a constant, so we're in good shape. My undergrad algorithms professor told me never to write a victory mark at the end of a proof. You have to like do a little square, but he's not here. Okay. Right, so now I see you, but we're a little low on time, so we'll save it for the end of lecture. Okay, so if we want to implement the selection sort algorithm, well, what do? Well, we're going to think of I as the index of like that red line that I was showing you before. Right, so everything beyond I is already sorted. So in selection sort, the first thing I'm going to do is find the max element between 0 and I, and then I'm going to swap it into place. Right? So this is just a code version of the technique we've already talked about. Hopefully this makes sense. Right? So you find the biggest element between 0 and index I. Right? That's what we're going to call j here. I swap that with the one in index I. That's step 2. And then step 3 is I still have to sort everything to the left of index I, and that's that recursive call. Okay, so if I want to justify the runtime of this particular technique, well now, let's call that t for time, yeah? Well, what do? Well, for one, I call selection sort with index I minus 1, right? So that incurs time that looks like this. But I also call that prefix max function. And how much time does that take? That takes order n time, yeah? So at the end of the day, I have some relationship that looks like this. Does that make sense? So by the way, notice that this order n kind of swallowed up the like order 1 computations that I had to do like to swap and so on. Okay, so remember there's this nice relationship, which you probably learned in your combinatorics class, right, which is that 1 plus 2 plus dot 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 plus n. Okay, I can never remember exactly the formula, but I'm pretty sure that it looks like n squared. Yeah? So based on that, and taking a look at this recursive thing, right, which is essentially doing exactly that, right? N plus n minus 1 plus n minus 2, and so on. I might hypothesize that this thing is really order n squared. So if I'm going to do that, then again, if I want to use the same technique for proof, I have to plug this relationship in, and then double check that it's consistent, right? So maybe I hypothesize that t of n equals cn squared, in which case I plug it in here. I have cn squared equals, with a question mark over it, cn minus 1 squared plus big O, or even theta of n here. So if I expand the square, notice I'm going to get c times n squared. plus a bunch of linear stuff, right? So this is really Cn squared. I should be careful with it. Minus 2Cn plus C plus theta of n. Yeah? Notice that there's a Cn squared on both sides of this equation. They go away. And what I'm left with is a nice consistent formula, right? That theta of n equals 2Cn plus, minus C. And indeed, this is an order n expression. So there's order in the universe. Life is good. Yeah, this is the substitution method. And again, I think you'll cover it more in your recitation. So what have we done? We have derived the selection sort. We've checked that it runs an n squared time. And by sort of this nice inductive strategy, we know that it's correct. So life is pretty good. Unfortunately, I promised for you guys on the slides that sorting really takes n log n time. And this is an order n squared algorithm. So we're not quite done yet. I'm way over time. So we're going to skip a different algorithm, which is called insertion sort. Also runs an n time. Where essentially insertion sort kind of runs in the reverse order, right? I'm going to sort everything to the left and then insert a new object. Whereas in selection sort, I'm going to choose the biggest object and then sort everything to the left. But I'll let you guys piece through that at home. It's essentially the same argument. And instead, we should jump to an algorithm that actually matters, which is something called merge sort. How many of you have encountered merge sort before? Fabulous. Good. So then I'm done. Okay, so let's say that I have a list. Now I'm sending a message back to Jason. I made this one up last night. So I have 7, 1, 5, 6, 2, 4, 9, 3. This is not in sorted order. But I can make a very deep observation, which is that every number by itself is in sorted order if I think of it as an array of length 1. Yeah? This is really deep. Like deep learning deep. Okay, so now what can I do? Well, I could take every pair of numbers, draw a little red box. Well, now they're not in sorted order anymore inside of the red boxes, so I'm going to sort inside of every box. In this case, not too exciting because it's just pairs. And now they're in sorted order because I said they were. Now I'm going to keep doubling the size of my boxes. So now, let's say I have box of length 4. What do I know about the left and right-hand sides of the dotted lines here? On the two sides of the dotted lines, the array is in sorted order, right? There's a 1 and then a 7, right? Those are in sorted order, 5 and a 6. That's because in the previous step, I sorted every pair. So when I merge these two sides together, I have an additional useful piece of information, right? Namely, that the two sides of the dotted line are already in sorted order. That's going to be our basic sort of inductive step here. Yeah? So in this case, I merge the two sides. I get 1, 5, 6, 7, and 2, 3, 4, 9. Then finally, I put these two things together, and I have to sort these two. I have to merge these two sorted lists, but they're in sorted order. Yeah, and that's going to give me a big advantage, right? Because oops, I lost my chalk. I suppose I've got space on this board here. Oh no. Right. So if I want to merge 1, 5, 6, 7, and 2, 3, 4, 9, there's like a nice, clever technique that we can do that's going to take just linear time. Jason tells me it's the two-finger algorithm. I think that's kind of a cute analogy here. So here are my two fingers. They're going to point at the end of the list. And I'm going to construct the merged array backwards. So how many elements are in my merged array if I'm merging two things of length 4? I don't ask you guys hard questions. It's 8. Yeah? 4 plus 4? 8? Yeah? OK. So what do I know? I know that my merged array, 5, 6, 7, has 8 elements. And now I'm going to have two fingers at the end of my array. Which one should I put at the end of the merged guy? The 7 or the 9? The 9. Right, thank you. Right? So now I can move my lower finger to the left, right? Because I've already added that. Notice that I never need to look to the left of where my finger is because they're already in sorted order, right? Now what should I add, the 4 or the 7? The 7. And so on, ... Yeah? So that's going to be the basic idea of the merge sort. I'm going to take two sorted lists, and I'm going to make a new sorted list, which is twice as long, by using two fingers, moving from the end backward. OK, so that's the basic intuition here. Indeed, there's our sorted list. It's stressing me out that there's no 8, but I needed a power of 2. So I think the merge sort we're going to present in kind of a backward way from the previous one, where I'm going to give you the high-level algorithm, and then actually the headache is that merging step, which I have 4 minutes for, and I apologize for it. So what does the merge sort do? Well, it computes an index C, which is the middle of my array, and it's going to make a recursive call, which says sort the left, right, which is everything between index A and index C, and then sort everything on the right, which is everything from index C to index B. I know this is confusing because usually letters appear in order. But C, if you think of as standing for center, then it kind of makes sense. Like, here's my array. I'm going to choose an index right in the middle. I've done myself a disservice by not using a power of 2, but that's OK. I'm going to say sort everything to the left of the dotted line first, sort everything to the right of the dotted line second. Now I have 2 sorted lists on the 2 sides of the dotted line, and then I'm going to use my 2 fingers to put them together. Okay, so that's what this is implementing here. See, there's 2 recursive calls, sort from A to C, and then sort from C to B. Oops, I didn't actually label this. So this is A, C, B. And then I got to call merge. Okay? Now, our implementation of merge, well, we can also do this in a recursive fashion, but I personally find this a little complicated, I'm going to admit. But here's the basic idea here, which I'm now rushing. Ugh. So I'm going to think of my upper finger as finger I, and my lower finger as finger J. Does that make sense? OK, so I have 2 sorted lists. So maybe like that. I don't know, 1, 3, 5, 7. And then I have a second sorted list here, which is maybe 2, 4, 6, 72, as one does. Then I'm going to have one pointer like this, which is I, and a pointer down here, which is J. Right? And my goal is to construct an array A with a bunch of elements in it. And the way that I'm going to do it is I'm going to use exactly the same kind of recursive argument, right? That I can either have the biggest element of my array be the last element of the first guy, or be the last element of the second one. Yeah? So here's going to be our recursive call. And in addition to that, for convenience, we'll have a third index, which is B, which is pointing to the sort of thing inside of my sorted array that I'm currently processing. Yeah? So it's going to start at A, go to B. Yeah? Incidentally, I see a lot of people taking photos of the slides. These are just copy-pasted from the course notes. OK. So in this case, what should I put in B? For my 2 arrays, I have 1, 3, 5, 7, 2, 4, 6, 72. 72, yeah? Great. So now what am I going to do? I'm just going to call the merge function, but I'm going to decrement B, because now I'm happy with that last element. And in addition to that, I'm going to decrement J, because I already used it up. And so that's our recursive call here, right? It's saying if J is less than or equal to 0, so in other words, I have an element to use in one of the lists or the other, and that maybe the left one is bigger than the right one, right? That's our first case. That does not apply in this example here. Well, then I should make the last element of A from the first list and then recurse with one fewer element I. And similarly, the reverse case for J. OK, so if we do our runtime in 2 minutes or less, bear with me, guys. Well, what is this merge function going to do? Well, in some sense, there's 2 branches, right? There's an if statement with 2 pieces, but both of those pieces call merge with one fewer piece in it, right? So in some sense, we have S of n equals S n minus 1 plus theta of 1, which we already know from our previous proof means that S of n is equal to theta of n. So in other words, it takes linear time to merge. It kind of makes sense intuitively, right? Because essentially you're touching every one of these things once with your 2 fingers. And now, our probably the hardest part of the lecture, which I left 0 time for, is deriving the runtime for the actual merge sort algorithm. And what does that look like? Well, that one's a little bit trickier, right? Because, of course, I call the merge sort algorithm twice, each time on a list that's half the size. In this class, we're going to assume that our list is always the power of 2 in its length. Otherwise, this analysis is a itty-bitty bit more of a headache. So first of all, how long does it take to sort an array of length 1? I legit am not going to ask hard questions. Everybody. Yeah, just like 1, right? Because like there's nothing to do. An array of length 1 has 1 element, and it's sorted. It's also, the biggest element and the smallest element. Okay. And now, what does our algorithm do? Well, it makes 2 recursive calls on lists that are half the length. Yeah. And then it calls that merge function, and we know that the merge function takes theta of n time. That makes sense? So one thing we might do, because we have some intuition from your 6042 course, is that we think that this thing is order n log n, right? Because it makes that 2 recursive calls, and then it puts them together. And let's double check that that's true really quick using the substitution method. So in particular, on the left-hand side here, maybe I have c n log n. Now I have 2 c, well, I have to put in n over 2 log n over 2 plus theta of n. And I want to double check that this expression is consistent. I've got about a foot to do it in. Okay? So remember, let's see, if we use our favorite identities from high school class that you probably forgot. Remember that log of 2 things divided by each other is the difference of the logs? Right? So this is really 2 divided by 2 is 1. So this is c times n times log n minus log of 2. Yeah, plus theta of n. I'm already out of time, but notice that there's an c n log n on the right-hand side. There's a c n log n on the left-hand side. So those 2 things go away. And what am I going to be left with? I'm going to be left with theta of n equals c n log of 2. Notice that c and log 2 are both constants. We have a theta of n on the left-hand side, so there's order on the universe, and we've derived our runtime. So I know I rushed a little bit through merge sort. I'm sure that Eric and Jason can review this a little bit next time. But with that, we'll see you, Thursday and Friday, and it's been a pleasure to talk to you all.